Hello everybody. In the last couple of lectures, we considered the curious behavior of the specific heat of solids. We saw that at high temperatures, the specific heat approaches a constant value, which is termed as a Dulong-Petit limit, and at low temperatures, the specific heat goes to zero. This interesting behavior was a puzzle for a long time until Einstein and a little later Debye came along and were able to very satisfactorily explain this behavior. Einstein introduced a very key quantum mechanical concept to explain this behavior, and he also used an atomic model of solids. In other words, he viewed the solid as composed of a collection of atoms. And Debye later on came along and fixed one little deficiency in the Einstein model. Debye in fact introduced the concept of the density of states. So in this lecture, we are going to attempt to explain what we really mean by this thing called the density of states. And so we are going to take a step back and view the solid as an elastic continuum, and we are going to use that construct to introduce several concepts such as wave vector and dispersion relations, and finally the density of states. Now, of course, although we are going to use the elastic continuum as a description of the solid to introduce the concept of the density of states, I should point out that this is a general concept that we will use time and again in the next set of lectures. This applies not just to elastic waves, but also to the behavior of electrons in solids. So that's the plan for today. So in particular, we are going to treat the solid in the long wavelength limit. This basically means that let us say we have a perturbation that is going through the solid, such as a wave, a sound wave, an elastic wave, and let us assume that the wavelength of this wave is much longer than the atomic dimension, than the interatomic distances. When the wavelength is much longer, much larger than the interatomic distances, you can ignore the specific details of the atomic level picture of the solid. The wave is so long that it kind of averages out the effect of the individual atoms. Under this long wavelength limit, we can disregard atoms and treat the solid as a continuum. And that's going to be the background for what we are going to do. So to start with, we are going to consider a 1D solid, a one-dimensional solid, let's say a rod with its axis along the x-axis. And we are going to watch for perturbations that course through this rod, through this 1D lattice. We are going to watch for displacements of infinitesimal pieces of this one-dimensional solid along the x-axis. So here is a rod along the x-axis, and we are going to define a variable u that describes the longitudinal displacement of an infinitesimal piece of this solid. So u of x is the displacement at x, and u of x plus dx is the longitudinal displacement at x plus dx. So once you know the u as a function of x at various values of x, we can actually define a strain that this solid is undergoing at various values x. So we can then apply Hooke's law to the solid, and we can also apply Newton's law to the solid, and that's what we're going to do next. So there is Hooke's law, where S is the stress, E is of course the strain that was defined earlier, and Y is the Young's modulus. So Hooke's law basically states that stress is directly proportional to strain, with the proportionality constant in this particular case being the Young's modulus. Let's now apply Newton's law. So Newton's law is F equals ma, where F is of course the force, m is the mass, and a is the acceleration. We can define, or we can write down F in terms of the stresses that we have just defined. S at x plus dx is the stress experienced at the location x plus dx, and S of x is the stress experienced at location x. The difference between the two stresses is is going to be related to the force that infinitesimal unit dx is going to experience when, of course, you multiply the difference between the two stresses by the cross-sectional area A. So S at x plus dx minus S at x, the whole thing multiplied by A, is actually the force. Likewise, we can write down the mass in terms of the density rho, and A is the cross-sectional area and dx is the infinitesimal length. So A dx is a little piece of infinitesimal volume times rho, that gives you the mass. And of course the acceleration is d squared u over dt squared. So we have, and of course note that A occurs on both sides, and so both the A's can be cancelled, and we have an equation now that represents Newton's law. So this last equation represents the dynamics of the section dx. By dynamics we mean how the section dx is going to behave as a function of time. So note that on the right hand side you have d squared u over dt squared, where t is the time, and so this equation prescribes the dynamics as a function of time of this infinitesimal section dx. Now we can actually use Hooke's law, which is S equals y times E, to actually write down the position dependence of the infinitesimal length dx as well. So we are going to now write down S of x plus dx minus S of x in terms of the Hooke's law. Let's see what we get. So there it is. All we have done in the first part of this equation is to write S minus S, the two stresses, as a differential, and then in the second part here we have just used Hooke's law. We have used the fact that S equals y times E, and we get ds over dx as y times dE over dx. And in this last part here we have used the definition of strain that we proposed earlier, that we wrote down earlier, where E was written in terms of U. So that finally gives the difference between the two stresses on either sides of the infinitesimal length dx as y times d squared u over dx squared times dx. So compare these two equations, this equation here which we got from applying Newton's law, and this equation here that we got by applying Hooke's law. Right, the right hand side of both equations have the time dependence over here and the position dependence over there, and so we can equate the two. Note that the a's can be cancelled out in this first equation, and so this part here of the equation without a can be equated to this piece, and that is going to give us what we call as the 1D or one-dimensional wave equation that represents this solid. So here is the 1D wave equation, and note of course that you have both time and position dependence built into this equation, and u of course is the infinitesimal displacement, rho is the density, and y is the Young's modulus. So this is the one-dimensional wave equation for our rod. We can now write down the general solution for this particular equation. So that's our general solution for this 1D wave equation. Note that the general solution of course is position and time dependent. A is an amplitude, which is a constant, and I is of course square root of -1. Q is called the wave number, and Q is actually equal to 2 pi over lambda, where lambda is the wavelength of this wave, and omega is of course the frequency. I want to point out something very interesting here. We have encountered something similar in one of the previous lectures when we talked about reciprocal space. Note that Q, the wave number, has units of 1 over length, right? And here it is equal to 2 pi over lambda, where lambda is the wavelength. q times x is of course dimensionless. So q is the dual of x. So x as units of length and q as units of 1 over length. And we saw this earlier, we'll also see today that under certain special circumstances, such as the imposition of periodicity, q will begin to take on specific values. Likewise, omega and t are duals of each other, right? T as units of time and omega as units of reciprocal time or hertz. And so omega and t are duals of each other. So I just want to make this point. Another point I want to make a note of is that this general solution that we are talking about here is also a representation of what people call as a propagating plane wave. So the next step is for us to substitute this general solution into our 1D wave equation. And when we do that, we will get a relationship between omega and q. So I leave it as an exercise for you to check the algebra here. When you substitute the general solution into the 1D wave equation, perform the appropriate derivatives, you will get this particular relation. Omega equals square root of y over rho times q. This relationship between omega and q is called a dispersion relation. And note that the square root of y over rho is a constant. Y is the Young's modulus, rho is the density. So these are constants of the material. And so omega is linearly related to q, with the proportionality constant being square root of y over rho. Let us make another interesting observation. We actually already know the relationship between omega and q. In fact, omega divided by q is nothing but the velocity of the wave in our solid. So we thus come to a very interesting result, not altogether unexpected or unanticipated though, since the velocity of the wave, Vs, which we're going to represent the velocity of the wave as Vs, is equal to omega divided by q. Omega is a frequency, q is the wave vector or wave number. We have Vs being equal to square root of the Young's modulus divided by the density. So we have a way of calculating the velocity of a particular wave in this solid, in this 1D solid. Now I'm going to ask you a question as to what kind of a wave this is. I'm going to pause for a moment for you to think about what type of wave we are talking about here. So this is nothing but the elastic or the acoustic or the sound wave velocity in this particular solid. So the sound wave velocity in any solid is basically proportional or is equal to the square root of the Young's modulus divided by the density. It's an interesting result. We can then plot what is referred to as the dispersion diagram, which is essentially a plot of the frequency versus the wave number. And in this particular case of an elastic solid, we get a straight line. And the slope of the line is, of course, the velocity of the wave. What we are going to eventually see is that in the large q limit, remember when q is large, the wavelength is small because q is proportional to 1 over the wavelength. Q equals 2 pi over lambda, where lambda is the wavelength. So when q goes to large values, it basically means that the wavelength is going to small values. We are going to see deviations from this linear behavior. And I'm going to pause for a moment and let you think as to why this would be the case. Why would we deviate from this linearity as q becomes large or lambda becomes small? The reason is that as wavelength becomes small, we are gradually approaching the atomic limit. We are gradually approaching the interatomic distances when the elastic view of a solid begins to break down. And so this linearity begins to get degraded. So there it is. So deviations from linearity, which are also called dispersion. dispersions. It happens at large values of q or small values of lambda due to the discrete or atomistic nature of solids. This becomes relevant as wavelength becomes small and approaches interatomic distances, when the elastic approximation no longer holds. Before we close this part of the lecture, I also want to make a note that everything we have discussed so far deals with longitudinal waves, right? Where the disturbance is along the same direction as the propagation, the wave propagation direction. We can also have transverse waves, in which case the disturbance or the displacement of those infinitesimal units that we discussed earlier is normal to the wave propagation direction. Under such circumstances, the appropriate elastic constant to use is the shear elastic constant rather than the Young's modulus y. In general, the elastic constant tensor describes wave propagation in anisotropic media. So we are inching our way towards the goal for this particular lecture, which is density of states. Before we get to that, we make one little stop, one more little prelude, and we're going to discuss this concept of the modes of vibration. In fact, these are what we call as states. Let's consider a bar of length L. We are already familiar with the situation, and we actually know the solution of the wave equation, elastic wave equation for this one-dimensional bar. For convenience, what we are going to do is we are going to suppress the time dependence. Remember, the time dependence was e to the I omega t. So we are going to leave that out, and it's justified because we can always imagine that we are looking at this bar at a particular time t, and we are looking at how the amplitude of the bar is varying with position at a particular time t. So you can suppress the time dependence, and when you do that, the solution of the wave equation is very simply given by this equation here. So u equals some constant a, which represents the amplitude, times e to the I q x. Next, what we need are boundary conditions. So one choice for the boundary condition is that the bar ends, the ends of the bar are clamped. They are not allowed to move, they are fixed in position. So under this assumption, under the assumption that the ends of the bar are clamped, are u at x equals 0 and u at x equals L equals 0 as well, because those 2 points, x equals 0 and x equals L, are clamped, and so they are fixed, and they are 0. The amplitude is 0. Another choice for the boundary condition, which we will use throughout this course, goes under the name of periodic boundary conditions, and let's very quickly see what we mean by that. So what does this mean? Essentially, it means that the right end or one end of the bar is constrained such that it is in the same state of motion, same state of vibration as the other end, the left end. It is almost as though the bar was deformed in a circular manner, such that the right end joins the left end. The right end is equivalent to the left end. So the consequence of this boundary condition mathematically is that u at x equals 0 is equal to u at x equals L. Note that the u at the two locations 0 and L need not be equal to 0 like in the previous boundary conditions. So the u's do not equal to 0, but they have to equal each other. Now this has a further consequence, and that's what we are going to see very quickly, and here it is. So if you go through this algebra, you will see that q has to essentially be an integer multiple of 2 pi over L. This is a consequence of the periodic boundary conditions that we have imposed. It's a consequence of periodicity. And what you're seeing here is essentially identical to what we encountered in our discussion of reciprocal space lattices and Fourier transforms. Now, let's make an important observation. So our Q has to have specific values for this periodic boundary condition to work. It has to be an integer multiple of 2 pi over L. An important consequence of this is that as L goes to infinity, of course 2 pi over L goes to 0, and so Q becomes a continuum. So the picture here shows the Q axis, and the grid points indicate the specific values that Q can possibly take, separated by 2 pi over L, of course. And as L tends to infinity, you can see that 2 pi over L goes to 0 and Q becomes a continuum. Now, here at this point, I would like to make an observation. Each of the Q values represents essentially a mode of vibration or a state. So this is an important definition, right? Each Q value represents a mode of vibration. A mode of vibration is essentially a pattern of vibration with a specific value of the wavelength. And bear in mind that Q is what we called earlier as the wave number, which means it's related to the reciprocal of the wavelength. So Q is actually 2 pi over the wavelength, and by that definition you can see that the wavelength of the modes of vibration are essentially L divided by N, where L is the length of the rod and N is an integer. So now we are ready to discuss the density of states, or the density of the modes of vibration. So essentially we are going to count how many modes of vibration we can possibly have in an infinitesimal range of frequencies at a particular frequency. That's essentially what the definition of what we mean by the density of states. So this is an important definition. So the density of states, or DOS, as it is affectionately called, is essentially the number of states or the number of modes occurring in the omega to omega plus d omega interval. So the density of states is a function of omega, right? So the density of states at a particular value of omega is essentially a count of the number of modes or number of states between that omega value and omega plus d omega, where d omega is an infinitesimal. We are now going to derive the expression for the density of states for our elastic waves. We are going to do it for 1D and 3D. We are going to start off by considering our Q space. Right? We already just learned about what possible values Q can have. So we're going to consider that Q space, and we're going to consider an interval dq in that Q space. Right? Then we're going to ask the question, how many modes are there? How many modes of vibrations are there in that dq interval? Now that is actually easy to write down because we have our infinitesimal dq, but we also know the distance between two possible Q points for our 1D bar. And that is nothing but 2 pi over L, right? So let's go back and quickly remind ourselves. Here is a picture. So here are the possible values that Q can take, and the distance between any two allowed Q values is 2 pi over L. So if we have a region dq, the number of possible Q points in that interval dq is nothing but dq divided by 2 pi over L. That's kind of what I'm saying over here. So we are now going to use the symbol g of omega to represent our density of states. And g of omega is going to be defined such that g of omega times d omega is the number of states or modes that lie in the interval d omega between omega and omega plus d omega. This may get a little confusing. Let's just write this down. Here it is. The right hand side is familiar. That's the number of modes in an interval dq. And the left hand side represents our density of states. G of omega is a density of states, but it's a distribution function, and so you need to multiply it by the infinitesimal d omega, such that g omega d omega is really the number of states between omega and omega plus d omega. So this equality has to hold, and note that we already know the relationship between omega and q, which is of course our dispersion relation. So this equation over here is something that follows from this equation. We just moved our variables around, and in the denominator we get d omega over dq, and as I just noted, we know the relationship between omega and q through via the dispersion relation, so we can write down that integral. Now I quickly stuck in this value 2 up front, and this 2 is to account for the positive and the negative q regions. Right? Okay, so let's take a look at this plot which attempts to capture most of what we've discussed. So this is a plot of omega versus q. The slanted lines of course indicate the dispersion relation between omega and q, and of course we already saw that the slope of this line is the velocity of sound, velocity of elastic waves in that medium. The little grid points along the q axis represent the allowed values of q, and they are spaced at a distance of 2 pi over L with respect to each other. And in this picture, using red lines, I'm also showing representing d omega. So so that's the d omega, and correspondingly this is our dq. And you can see that a bunch of q values are allowed, and that basically translates to a bunch of allowed omega values. So using this picture, and again, okay, another point I want to make a note of is the positive and the negative q region, which is why we stuck in this 2 over here. So after substituting the value for d omega over dq, which we know, remember we 15 minutes or so ago, we noted that d omega over dq, the slope of those slanted lines is related to the velocity of sound, and so that term is down here in the denominator. And so we have our density of states expression for our 1D bar. So this is an important relationship which we want to bear in mind. An important point to note is that our density of states g of omega is a constant. It is a constant that is independent of omega in this particular case. It's a constant because L, of course, is a constant. It's the length of the bar, and Vs is the velocity of sound in the material, which is also a constant, and of course pi is a constant. So g of omega is really a constant for this one-dimensional example. This is not, of course, surprising. If you just simply look at this dispersion relation, the omega versus q behavior from this plot, you will see that as you keep going up in omega, the number of states that keep getting added to the system is of course being done at a constant rate, and so it is no surprise that the density of states at any given value of omega is actually independent of omega, and it's a constant. That's in 1D. What about higher dimensions? Now what we are going to do is we are going to very quickly extend all these notions to a three-dimensional situation. So here is the solution of our wave equation in 3D. It's just a mere extension of what we already saw. Instead of q and x being scalar quantities, now we need to replace them appropriately with vector quantities, and so the solution of the wave equation with the time dependence suppressed is of course a times e to the I q dot R, where Q and R are vectors. Now we are going to impose the periodic boundary condition to this system, assuming that the three-dimensional analog of our one-dimensional bar is now a cube of side length L. So we assume that our system is a cube of side length L. We impose our periodic boundary conditions. I leave it as an exercise for you to show that this is indeed the result. So we get that result, and the consequence of that result is that our Q's, the Qx, Qy, Qz, the three components of our Q vector, have to be integer multiples of 2 pi over L. So n, m, and L are integers, and these are the specific values that each component of Q can take, of course, independently. So, remember, in the 1D case, our Q space was composed of a Q axis with specific values that Q could take along that axis, spaced by 2 pi over L. In this 3D case, our Q space will be a 3D grid with the grid points, of course, spaced by 2 pi over L. So given that insight, we are going to write down the volume occupied by one Q point, the net volume that one Q point actually occupies. So that's our next exercise. So okay, so the volume per Q point is 2 pi over L cube. We now ask the important question: how many modes do we have inside a sphere whose radius is Q? Remember, we asked a similar question with the 1D case. We asked how many modes do we have in a infinitesimal dq. So here we are going to get to that, but before that we ask the question, how many modes do we have inside a sphere whose radius is Q? To help us with this question, to help us answer this question, we have this little cartoon to your right. So to make my life a little bit easier, I have shown just the 2D section of this 3D Q space. You can see Qx and the Qy axes, and the points are the allowed values of Q, and they are spaced by a distance 2 pi over L. And we are asking the question, how many modes do we have inside a sphere whose radius is Q? So here are a couple of steps that will take us to our goal. Volume of the sphere is, of course, 4/3 pi Q cubed, and volume per point is something we already wrote down, 2 pi over L cube. So the number of modes inside the sphere whose radius is Q is just the ratio of these two expressions. Let's write that down. So there it is. So all we have done is find the ratio of the volume of the sphere versus the volume per point, and we have defined a new variable V, which is just L cube. So V is the volume of our material. So this is the number of points within a sphere of radius Q. Now what we are really after is the number of points in the sliver of this sheath, spherical sheath of thickness dq, in analogy with what we did with the one-dimensional case. So the question is, what is the number of points in that sliver dq? That's actually easy to do. We just find the first derivative of this expression that we just wrote down with respect to dq, and that's really all we need. We then need to equate that differential to g of omega d omega, just like we did before for the 1D case. And I'm just going to write down the results. Okay, so there it is. All we have done is we took the first differential of this quantity over here. That gives us the number of states, number of modes in a sheet of thickness dq, and that has to equal to our g omega d omega. So that gives us this first expression over here, and then we use the dispersion relation, right? The relation between q and omega, which is essentially going to be related to the velocity of sound, and we are able to change that to this and change that to this. And this is going to take us to our final result. So now we can write down the expression for the density of states in 3D. So this is our final expression. We box it, our density of states in 3D. And we have stuck in this factor 3 up front in this expression, in this equation on the right hand side, to account for the fact that in 3D we have one longitudinal and two transverse modes. So one longitudinal plus the two transverse modes account for that factor 3 up front. So we will visit longitudinal and transverse modes eventually when we talk about phonons. But for now, I would like to make the very important observation that the density of states in 3D displays a quadratic dependence on omega. Now, g of omega is proportional to omega squared, whereas in 1D it was a constant. And that behavior, this interesting difference between 1D and 3D, is actually shown in this plot schematically. It is left as an exercise to figure out how a two-dimensional system would behave. Now at this point, I would like to draw your attention back to our discussion on specific heats. When we talked about the Debye extension of the Einstein model, we noted that Debye used the proper behavior of the density of states of a three-dimensional solid. At that time, I noted that the density of states is going to be quadratically dependent on omega, and that time I stated that without proof. But in this particular, somewhat of a long lecture, I have provided the proof that g of omega is proportional to omega squared. This is the correct dependence, and if you use this dependence in the Einstein model, if you modify the Einstein model to account for this dependence, you would get the correct dependence of the specific heat as temperature goes to 0. So this is perhaps a good time to go back and revisit those lectures on specific heat. That concludes our lecture for today. Thank you.